Good morning, everybody. Jenya here. Today I'm with Daryl Killen. Daryl is a registered professional forester with the Institute of Foresters of Australia and a member of the Carbon Market Institute. He currently supports carbon abatement projects in savanna burning and has a project growing native conifers as a carbon sink on the Atherton tablelands. Daryl has been working full-time in carbon farming since 2011 and is passionate about increasing the value of carbon at the farm gate. Thanks very much for joining us today, Daryl. Please take it away.
Thanks very much, Genia, and hello, everyone. Yep, my name's Daryl, and I'm a forester. As Genia said, I went through Melbourne University, graduated in 1993, and I've been working in far north Queensland ever since on a range of projects. Behind me today, you've got some kauri pines, Agathis robusta, that were planted in the 1930s on the Atherton tablelands. I'll just share my screen. So today we're going to talk about measuring carbon in forests, and we have been involved in the first registered carbon sink for tree planting since 2012. Our native conifers carbon sink is planting a range of conifers and biodiverse plantings, and our first planting was in 2013. We're planting three main conifers: hoop pine, kauri pine, and bunya pine, and other rainforest species as well. Here's a picture of the Bunya Mountains, where 300-year-old plus bunya pines grow as an overstory with a rainforest understory. And that's the kind of system we're trying to recreate here on the Atherton tablelands with our project. On the right-hand side there, you'll see some large nuts there, which are the bunya pine cones, which can weigh up to 15 kilo. And on the right-hand side, down the bottom there, there's a natural stand of kauri pine near one of the creeks here in the wet tropics. So as a picture of our first planting site, our pilot project, where we're reforesting a small area to get all of our systems correct and our processes in place. You'll see the creek line through here. This can be planted up with biodiverse species, and then the conifers are on the slopes. Here's a picture of our 2017 plant, and here's what it looked like beforehand. So we're targeting grazing land on the Atherton tablelands. We plant biodiversity in the creeks here, as you'll see, and here is a picture of a fence line that was about 5 years ago pulled up, and the left-hand side was grazed and the right-hand side wasn't grazed. So the right-hand side is what happens in conifer plantations, that can happen in conifer plantations after a few decades of removal of grazing. You start to get biodiverse understory. I'm going to talk a little bit about the plantation forestry method because it's under review this year with the Clean Energy Regulator. It's one of the 30-odd methods involved in Australia for doing carbon farming. This is a complicated diagram that you can look at later, but there's a number of ways you can plant trees under this method. So techniques for measuring carbon. We have modelling versus direct measurement. Most models rely on direct measurement, of course, to begin with, and direct measurement is going out and actually measuring heights, diameters, volumes of trees in plots, and those data sets then get used to form the basis of models that are then utilised by the industry to calculate carbon. There are a range of ways of measuring carbon, including satellite, aerial photography, which is traditional aerial photography with, say, fixed-wing aircraft, and then you have drone-based options, and we also have ground-based. I'm going to focus a bit on the ground-based today. So this is all about where the rubber hits the road and how we actually need to have more precise measurements to calibrate those other methods of forest inventory. All of these methods involve sampling design, defining your strata and the boundaries for strata, which are called carbon estimation areas. They involve data collection. We have growth in our FullCAM model that I'm going to talk about shortly, but there's no yield, and I'll explain what that means a bit later. And then we also have analysis and reporting requirements in carbon farming. So old school measuring forests involves getting a diameter tape and a height stick and going out in the field and measuring your diameter at breast height, which is 1.3 meters above the ground, and calculating the volume through having the basal area, which is the cross section of a tree looking from above, multiplied by the height. And there's a factor in there. So diameter at breast height divided by 200. You'll see the formula there anyway. So if a tree is 22.7 meters tall and 42.6 centimeters in diameter, the total volume is 42.6 divided by 200 squared times 3.142 pi multiplied by 22.7 divided by 3. So 1.03 cubic meters. This assumes the conical shape of the tree. So that's how we all started out hundreds of years ago. Of course, in Europe, forest inventory was pioneered, and that is the old school way of measuring volume of a tree. Nowadays, we use what's called FullCAM, which is the full carbon accounting model for Australia. And this is a national system based on the national carbon accounting system, which was developed in 20, 30 years ago. And there are permanent plots established all over Australia since 1970. And those permanent plots, the data from those plots is used to build up this national effective model to measure carbon. It's based on a point source rather than area-based model. And the latitude and longitude of the site you put into FullCAM, and it literally tells you how much carbon you generate for that area, that point. It's based on maximum above ground biomass. There's the theory that in any particular site, there's only so much biomass that site will sequester, if you like, or grow. And it depends on your configuration of tree planting systems, whether or not you attain that maximum biomass. So we can't go above the maximum according to FullCAM, but we can in reality. So you might have a particular site that generates more volume than FullCAM gives you, but you're not able to claim that in your carbon farming at the moment anyway. So FullCAM measures change in carbon stock over time. So we're measuring how much carbon is there between a point in time and another point in time. And we convert that into certain carbon estimation areas. And it uses what's called, the basis of this is stratified random sampling that projects have undertaken and can undertake, where you define your strata and then you have sampling within that. So that's the foundation of every forest inventory program. And then FullCAM models different management inputs and scenarios. So you can put in parameters such as your fertilizer and weed control events, and pruning and thinning activities that can then be modeled, and FullCAM shows the change in that carbon stock over time. So there's the FullCAM program components, and I apologize for the quality of that picture there. It's a Microsoft-based Excel with, for those interested in the code, 3PG, CAM4, GenDeck, and ROS-C are the software used in the model. And it includes parameters such as the growth from light that comes into the area. It has tree components, debris, and litter. The tree components include the actual standing tree volume. There's a component in there for soil carbon as well. And then it has the capacity to include carbon stored in wood products that we might remove from the plantation. It's based on what's called allometric equations. So you can have a drop down for species such as hoop pine that actually have what's called an allometric equation that defines the volume for that area. And of course, it has statistical integrity. So here's a full cam example from our native conifers scenarios, and you'll see here the change in volume over time. So on the x-axis, we have years, 0 to 100. On the y-axis, we have tons of carbon per hectare. So that's tons of carbon, not tons of carbon dioxide. That's important to distinguish between those two. You'll see here, the blue line is a hoop pine stand with 7 weed controls. And then the lighter, this more aqua color is hoop pine with 7 weed control plus 1 prune plus 2 thinnings. And that is showing here where we remove some trees, we might reduce the stocking initially. And you'll see a growth response going up through there. Then there's a second thinning, and there it drops back down, and then the trees start growing again. And then there's the final harvest at age 60. And this includes a component, this trailing carbon includes some of the carbon in the wood products. Now, this purple line is a comparative, this is a different method. Rather than using the plantation forestry method, this is the mixed species environmental planting, sorry. This rather than hoop pine, it is mixed species. So this is a range of rainforest species, and that's the volume over time. So you'll see here that mixed rainforest species generate about 300 tonnes per hectare, and with hoop pine, you get over 450. And by combining these two different systems, we can end up with an intermediate result. So the problem with full cam is that it doesn't always reflect what we're doing on the ground. So for example, those hoop pine equations assume that we're planting a monoculture of hoop pine, whereas we might want to plant a number of species to increase the biodiversity. So in order to do that, there are new techniques to more accurately and precisely measure volume in standing trees. This is a LiDAR output. So LiDAR is laser scanning, and you'll see here, this is the Kauri pine plantation, and this is the scan position here. We had a tripod with a laser scanner, and this particular scanner puts out 3 million pulses per second that then bounce off up to 7 times. So the actual unit is generating up to 21 million data points per second. And this output that you get enables you to have a completely precise measurement of tree volume. Now, full cam doesn't currently allow us to use LiDAR, but the reason I'm showing you this is to reflect or to demonstrate that actual carbon generation can be higher than full cam. And the sorts of laser techniques are likely to be incorporated into the national counts in the near future, which will make carbon measurement more precise. And we've obviously come a long way from using just diameter and tree height manual measurements. Here's the LiDAR unit here. This is a Regal unit on a tripod. And this spins around, and the